Next, let's talk about the area problem. So what we want to be able to do now is calculate the area under a curve. And this is something that calculus is going to help us with. We're going to start developing that process here. So what we want to do to begin is divide the region into a series of rectangles that either fit just inside the region or just outside the region. Then sum the areas of these rectangles to approximate the area of the region. Now, by increasing the number of rectangles, you can obtain closer and closer approximations of the area of the region. So it says let f of x be non-negative on the interval a comma b. Find the area of the region lying beneath the curve y equals f of x and above the x-axis from x equals a to x equals b. So what we want to do is divide our interval into n equal subintervals having width delta x. So if we want to approximate the area under the curve here, we could divide this into a certain amount of even rectangles. And as we draw our rectangles up here, if we were to find all of these areas and add them together, we would get an approximation for the area under the curve. Now, as we increase the number of rectangles, this is going to give us a better approximation of the area under the curve. If you look at these rectangles, they're all above the curve, and so this extra space out here is going to give us an overestimate. We actually call this an upper sum. If the rectangles were drawn underneath the curve, well, then it would give us a lower sum because it's an underestimate. Well, we have to remember to find the area of a rectangle. Remember, it's going to be length times width, or base times height. So the width is given right here, b minus a over n. So this is your width, b minus a over n. And notice that it's the same for all of these because it's an equal width. And then the height of each of these is going to be found by the y value at each of these x values. So you find the x value, and then you find the y value, and that is the height. So find your x value, plug it into the function, gives you the height. So we would be able to find all of these areas of the rectangles and add them together. So let's try this in example 4. It says use the 5 rectangles to approximate the area of the region bounded by the graph of f of x equals 6 minus x squared, the x-axis, and the lines x equals 0 and x equal 2. So here we have our drawing, and you can see our rectangles. So the first thing we need to do is find the width of each of these rectangles. And that's going to be b minus a over n, so it's going to be 2 minus 0 over 5. So notice here that b is right here, and a was right here, and we have a total of 5 rectangles. So each width is actually 2/5. Now we need to find the height of each rectangle. And that's going to be given by these y values right here. So looking at the x values that we have, we know the width is 2/5. So it's going to be 2/5 right here, and then 4/5 here, and 6/5 here, 8/5 here, and 10/5 right here. And so what we get then is the width of 2/5 times the height, which is actually going to be f of 2/5. And that would give us our first rectangle. Our second rectangle, notice it has the same width, and the height will be f of 4/5. For our third rectangle, notice the same width times our height of f of 6/5, and then plus 2/5 our width times the height of our next rectangle, which is f of 8/5, and then plus 2/5 the width times the height of our last rectangle, which is going to be f of 10/5. So you can see these are all being multiplied by 2/5. So we'll go ahead and pull that out, and then we'll find our function at all of these values. So it'll be 6 minus 2/5 squared plus 6 minus 4/5 squared plus 6 minus 6/5 squared plus 6 minus 8/5 squared plus 6 minus 10/5 squared. Now you can type all of this into your calculator and you're going to come up with an approximation for the area of about 8.48. Now that's sort of a tedious process, which is why we're going to learn the limit of our summations. So we can see that we could have written this as a summation, and it would have been the sum as I equals 1 to 5, because we had 5 rectangles. And what we could have done is had our height, which would be f of 2I over 5, or 2/5 times I, and then times the width, which is 2/5. And this would have given us our summation from I equals 1 to 5 of 6 minus, well, we would have plugged 2I over 5 squared, and then times 2/5. And then we could have found our sum using our n formulas, just like we had done before. So we could have squared our 2I over 5 and factored out our 2/5. So we'd add 6 minus 4I squared over 25. And then we could have used our summation formulas, and we would have gotten 2/5 times 6 times 5, and then minus 4 over 25 times 2 times n, which is 5 cubed, plus 3 times 5 squared, plus n, which is 5, and all of this over 6. And we could have used a calculator here, and we would have actually come up with the same answer of 8.48. So you can use either way you'd like there to approximate the sum of the area under the curve using those rectangles.
All right, next we want to look at something called Riemann sums. And basically that process of looking at the area under a curve and dividing it up into rectangles is the process of finding a Riemann sum. So you can see there's lots of different types depending on how you break up the rectangle. You can have left Riemann sums where the endpoint is on the left side of the rectangle, and that's kind of where it touches the function. You could have midpoint Riemann sums where the midpoint of that rectangle touches the function, or you could have right Riemann sums where the right endpoint touches the function. So we want to use these Riemann sums to approximate the area of a region under a curve. So here's the curve 12 over x, and we want to go from 1 to 4, and we want to let there be 3 rectangles. Okay, so essentially we're going to go from 1 to 4, and we want to split this into 3 equal rectangles. So we're going to see that this is going to happen here at x equals 2 and at x equals 3. Now, when we draw our rectangles here, we're going to want to use left endpoints and then right endpoints. So if we use left endpoints, that basically means that the rectangles have to touch the function on the left side here. So this one will come across and down, here and here. So this would be a left endpoint Riemann sum. So we basically just need to find the area of each one of these rectangles and then add them up. So if you look, going across here, the width of each one of these, since we're going from 1 to 4 and we're splitting that into 3 equal pieces, we know each width has to be 1. So 1, 1, and 1. Now all that's left to do is find the heights of each of these. So the heights occur at these different x values here. So this one will actually be f of 1. This height will be f of 2 because it's 1 away. And this height will be f of 3. Okay, so we can find those heights then by plugging it into the function 12 over x. So basically, we're going to want to do 12 over 1 for f of 1, plus 12 over 2 for f of 2, plus 12 over 3 for f of 3, and then multiply all of that by the width of the rectangle, which is 1. Okay, so ultimately here we have 12 plus 6 plus 4 for a total of 22. All right, next we want to try this with right endpoint rectangles. So we're still going from 1 to 4, breaking it into 3 equal pieces, but now we want the right endpoints to be the ones that are touching. Okay, so now our rectangles actually fall below the curve. So now we just need to find the area of all 3 of these. Notice the width is still 1, but now our height is based on that right endpoint. So this is going to be f of 2, f of 3, and f of 4. So we're going to have 12 over 2 plus 12 over 3 plus 12 over 4, all that multiplied by the common width of 1. So all in all, we're going to have 6 plus 4 plus 3, or 13. Now when you think about these Riemann sums, the one on the left here was an upper sum because all of the rectangles fell above the curve. So this is an overestimate. And then the one on the right here, this is a lower sum because you can see all the rectangles fell below the curve. So this is an underestimate. So we know the actual area is going to be somewhere between 13 and 22. Okay, so you can kind of see that right here with upper and lower sums. Upper are all above, where lower are all below. Now what happens then is sometimes you can't have always left or right endpoints. It's not always going to be so nice and neat as that. But the way it works with Riemann sums is it doesn't matter if you have upper or lower sums because eventually the limit is going to approach infinity where we have an infinite amount of rectangles. So it really doesn't matter if you're on the left or the right, if they're the same, because there's going to be so many in here that it isn't even going to matter.
So next we're going to talk about using the limit definition to find the area under a curve. In this case, we want to find the exact area under the curve. So it says let f be continuous and non-negative on your interval a to b. Then the area A of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a is given by a equals the limit as n approaches infinity of the sum where I goes from 1 to n of f of a plus b minus ai over n times b minus a over n. And what we have here, when you analyze this, is the height of your rectangle. And then this right here is the width of your rectangle. And if we add all the heights and the widths multiplied together, so each rectangle, and you let n go to infinity, you're actually getting an infinite amount of rectangles, which is going to give you the exact area of the graph. So in example 5, it says find the area of the region bounded by the graph of f of x equals x squared and the x-axis between x equals 0 and x equals 1. So let's go ahead and find our width and our height of our rectangles. So the width, remember, is b minus a over n, which in this case will be 1 minus 0 over n, which is 1 over n. And our height is going to be f of a, which is 0, plus b minus a, which is 1 minus 0, times I over n. And let's go ahead and simplify that there. So we actually are left with f of I over n. And now let's go ahead and plug it into our function x squared. So it really becomes I over n squared, which is I squared over n squared. So now we have our height and our width. So our area is going to equal the sum from I equals 1 to n of our height, which is I squared over n squared, times our width of 1 over n. Now we can multiply our height and our width together. So we actually have I squared over n cubed. And then we can actually factor out our constant. So we have 1 over n cubed times our sum of I squared. And now we can use our summation formula, and we'll have 1 over n cubed times 2n cubed plus 3n squared plus n, so that's the summation formula for I squared, over 6. So that was using the summation formula for the I squared. And now we'll go ahead and multiply here. And so we get 2n cubed plus 3n squared plus n over 6n cubed. Now if we want to find the area under the region, we're going to take the limit as n approaches infinity. And here you can see the exponents are the same. So we're going to divide coefficients. So we have 2 over 6, which equals 1/3. So what that's telling me is the area under this curve is equal to 1/3. So pretty powerful. It increases our ability to find the area of a bunch of different random shapes. Using our limits and our sums, we're able to find that exact area. All right, I want you to go ahead and try the next example on your own. Follow the same process there. Go ahead and pause the video and come on back when you're done to check your work. All right, welcome back. Here I have my formula written out there. Here you can see I substituted in my 1 plus I over n into my function, 4 minus x squared. And I went ahead and squared that binomial in this step. In this step here, I just did the 4 minus the 1 right here. And here I showed a little bit more work than I did in the example. What I did is separated this out. I distributed the 1 over n, so all three terms, and then showed that it was the sum of each of those separately. Again, you could skip that step, but now I can see that I have the sum of a constant, which is just going to be that constant times n. Here you can see I have the sum of I, so that one's going to be n squared plus n over 2. Here you can see I have the sum of I squared, and that's going to be 2n cubed plus 3n squared plus n over 6. And then you can see all of the constants just follow along right out in front there. Okay, then I still have that limit tagging along there. Then I went ahead and simplified a little bit, so 1 over n times 3n is just 3. And here I just multiplied these together. Again, I'm showing a little more work than what's necessary. And then here I showed the multiplications right here. Okay, from there you can use Bobo-Bot needs DC. Well, this is already a constant, so that if n changes, it's still going to be 3. So we get 3 there. Here the exponents are the same. Okay, you can see the 2 and the 2 are the same. And so this is going to be negative 1. Here the exponents are the same again, and so we have negative 2 over 6, or negative 1/3. And I just did a common denominator to add these up. We get an area here of 5/3. Okay, so again, the area under this curve, bounded by line x equals 1, x equals 2, and the x-axis, is going to be equal to 5/3.